Differentials are another aspect of using the slope of the tangent line. Differentials are applied when there's a nominal operating point or a nominal value to the function, such as, say, at x naught, there's a corresponding y naught on the black function here, f of x, and a little chunk of the tangent line is this red line. And when we're talking about differentials, we're not using the entire tangent line itself, but just the slope to predict if you are at a particular operating point or nominal point, what if the input changes just a little bit? Thinking of the x as the input and the y as the output in a system. If x changes a little bit by, say, delta x, then the input have changed from x naught to x naught plus delta x. And the question is, what would you expect the output to do of the function f of x? One way to find out what happens is to simply put the new x value of x naught plus delta x into the function itself, and you can find out what the new value is of the function, and you can see then how much it changed. You can calculate the new input value minus the old output value, and that is what we call delta x, or the increment, the incremental change in the value of the function. The problem may be that the function's hard to evaluate, or slow to evaluate, or costly to evaluate, and it would be interesting to be able to estimate that using the tangent line slope. So from the nominal, if we again displace the input by delta x and ask what would the tangent line say was the change in the output, that's what we call dy, the differential change instead of the incremental change. The incremental is exact. The differential is based upon the slope of the tangent line at the point that is the nominal point. So in this case, if you follow the slope of the tangent line at x naught y naught, you end up somewhat below the actual value of the function itself, and therefore you have an error. It's dy minus delta y, which gives you a negative error, and which is what we're seeing here in that the dy estimate is below the delta y actual value. The slope of the tangent line is just the sensitivity of the function at this point to a change in the independent variable. It's dy over dx. And if the input changes by delta x, if you multiply that delta x by the derivative at that point, the sensitivity to a change in delta x, then you will find the change in the y value based upon the tangent line, or the slope of the tangent line estimate. Take a specific example. Let's say that we take the parabola y equals x squared, which that turns out that actually is, and we take x naught as being 1 and delta x as being 0.5, that is x naught plus delta x is 1.5, and we can ask what is the equation of the tangent line, which is the linearization question, and the answer to that is the linearization is y naught plus the slope times x minus x naught. And in this case, it looks like the equation of that red tangent line is 2x minus 1. Now, in this case, we're not really interested in the tangent line itself, but only the slope of the tangent line. So we're only interested in the derivative. To estimate the increment, that is the actual delta, the true change in the curve itself between the x naught input and the x naught input displaced by delta x, you would simply have to calculate the x naught value of the dependent variable and the x naught plus delta x value and subtract them. In this case, delta y, or the increment, is f of x naught plus delta x, which in our case f is the squaring function, and x naught plus delta x would be 1 plus 0.5 would be 1.5, and from that you subtract 1 squared, and this gives us a value of 1.25. That's the actual difference in the output if you change the input from 1 to 1.5. The differential estimate of that is based upon the slope of the tangent line, which is f prime of x naught. That's the slope. If you multiply the slope, rise over run, by how much run you've got, you get how much rise you have. That's the differential estimate. And that is, in this case, an underestimate of the actual value of the function at the changed input. And the error would be the difference between the actual value and the value estimated by using the slope of the tangent line at that point. In this case, the error, and usually we're interested in the absolute error, that is, we don't really want to know whether it's positive or negative, we just want to know how much of it there is, and that is the absolute value function here. So the absolute value of dy minus delta y, in this case, turns out to be 0.25, which is the error you get if you use the slope of the tangent line at the operating point instead of the actual function to calculate the change in the output.